You think galaxies are fixed, eternal islands floating in the cosmic dark. They're not. They crash. They tear. They consume each other at speeds your mind can barely hold. Right now, today, galaxies are smashing together at over 3 million kilometers per hour, ripping stars from their homes and igniting firestorms of newborn suns that won't stop until every gram of gas is burned. This isn't ancient history. It's happening as you read this. And it's coming for us. Every spectacular type of galaxy collision explained. No speculation. Just the physics of what happens when 300 billion stars meet 300 billion more. The William Herschel telescope caught it in November 2024. NGC 7318b slamming through Stephan's quintet at 2 million miles per hour. That's over 3.2 million kilometers per hour. Not drifting, slamming. Lead researcher Marina Arnadova from the University of Hertfordshire said it straight. This created a shock akin to a sonic boom from a jet fighter. The Weave spectrograph on La Palma tracked the violence. When the shock moved through cold gas pockets, it went hypersonic, several times the speed of sound in intergalactic space, powerful enough to rip electrons from atoms. Glowing trails of charged plasma left behind. The data came from Weave combined with the low-frequency array, the Very Large Array, and James Webb. That's published in monthly notices of the Royal Astronomical Society in November 2024 by a team of over 60 astronomers. Stephan's quintet was discovered in 1877, 147 years of staring at wreckage. Now we see it live. When the shock passes through surrounding hot gas, it weakens dramatically. PhD student Soumyadeep Das at the University of Hertfordshire confirmed it. Instead of disruption, the weak shock just compresses hot gas, creating radio waves picked up by LOFAR. Two natures, one collision, hypersonic destruction in cold zones, quiet compression in hot zones. That dual behavior was unknown before November 2024. If you value documented astrophysics and collision mechanics like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from the William Herschel telescope. Weave first light observations published in monthly notices of the Royal Astronomical Society in November 2024 under lead authorship of M. Monhauers. Sakrais, Arnadova, and team, alongside data releases from NASA's James Webb Space Telescope from August 2024 SEWER and Hubble Space Telescope archival imaging programs dating back to 2002. These are not popular science summaries. These are peer-reviewed observational papers with specific photometric measurements, spectroscopic velocity data, and shockwave propagation models. Now back to the information. The antennae galaxies show you what happens after. NGC 4038 and NGC 4039. In the constellation Corvus, 600 million light-years away depending on the measurement. Some studies say 70 million using older photometry. Others say 43 million based on red giant branch analysis from 2008. The collision started about 1.2 billion years ago when these were separate spirals. NGC 4038 was barred, NGC 4039 was a clean spiral. 900 million years ago, they began their approach, looking like NGC 2207 and IC 2163 look today. 600 million years ago, they passed through each other for the first time. The pass created the tidal tails, 200 to 300 million years old according to formation models. The tails stretch out like insect antennae. That's where the name comes from. William Herschel found them in 1785. Hubble caught over 1,000 bright young star clusters bursting into existence in the wreckage. These aren't diffuse regions. They're superstar clusters. Each one contains tens of thousands to millions of blue newborn stars. The orange cores in Hubble images are the original galaxy centers. Old stars crossed by brown dust filaments, the blue knots scattered everywhere. Those are star formation sites surrounded by glowing hydrogen gas, appearing pink in true color images. Nearly half the faint objects in antennae images are young clusters. Age dating shows only 10% will survive beyond the first 10 million years. Most will disperse, their stars blending into the smooth galactic background. About 100 of the most massive will survive as globular clusters, like those orbiting the Milky Way. 4 supernovae observed in NGC 4038, SN 1974, E discovered by Miklos Lovas on March 21st, 1974, type unknown, magnitude 14, SN 2004 GTE, type IC, magnitude 14.9. Discovered by Berto Monard, December 12th, 2004, SN 2007 SR, type IA, magnitude 12.9, Catalina Sky Survey, December 18th, 2007, SN 2013 DK, type IC, magnitude 15.8, Chase project, June 22, 2013, 1 in NGC 4039, SN 1921, A, type unknown, magnitude 16 Inc., discovered by Edwin Hubble and John Charles Duncan in March 1921. 5 explosions recorded. Hundreds more happened unseen. Chandra X-ray Observatory found massive amounts of neon, dark pars, magnesium, and silicon when it analyzed the collision zone. Heavy elements necessary for rocky planets. The clouds contain 16 times as much magnesium and 24 times as much silicon as the Sun. That's planet-building material scattered across 150,000 light-years. The whole Milky Way would fit inside the antennae's outer ring. The mice galaxies deliver a different violence. NGC 4676 and Coma Berenices. William Herschel cataloged them March 13, 1785, with his 18.7-inch reflector at 20 feet focal length in Slough, England. He noted faint, much extended in the direction of the meridian. His son John saw 2 nuclei, noted extremely faint. Query, if not bicentral. John Dreyer added them as NGC 4676 in 1888. Rudolf Spittler at Wien University Observatory saw them with the 27-inch refractor, March 3, 1892. Identified 2 separate objects added as IC 819 and IC 820, 300 million light-years away. Some measurements say $290 million, others $345 million. Computer simulations by Josh Barnes at University of Hawaii and John Hibbard at National Radio Astronomy Observatory in Charlottesville show we're seeing them approximately 160 million years after their closest encounter. The long, straight tidal tail extending from the right galaxy measures over 300,000 light-years. It only looks straight because we see it edge on. It's actually curved. The tail is populated with clumps of young hot blue stars, separated by fainter material regions. Those dim gaps suggest the clumps form from gravitational collapse of gas and dust that once occupied those spaces. Some clumps have luminous masses comparable to dwarf galaxies orbiting in the Milky Way's halo. The bright blue patch in the left galaxy resolves into a cascade of star clusters triggered by tidal forces. Streams of material flow between the 2 cores. Spectroscopic study in 2007 found 10 young star clusters with ages less than 10 million years. 2 clusters in the tidal tails measured about 170 million years old. That timing matches the collision model. The galaxies are members of the Coma cluster. Confirmed physical members in 1961 when velocity measurements showed similar recession speeds to other cluster galaxies. They'll merge eventually. Hundreds of millions of years still to go. The stars and gas in the tails will either fall back into the merged core or orbit in the halo of the new elliptical galaxy. Hubble's Advanced Camera for Surveys captured them April 7, 2002 in blue, orange, and near-infrared filters. The Cartwheel Galaxy demonstrates the bullseye collision, ESO 350-40, also PGC 2248 and bigger, 500 million light-years away in Sculptor. D25 isophotal diameter of 57.69 kiloparsecs, 188,200 light-years across, mass between 2.9 and 4.8 billion solar masses, outer ring circular velocity 217 kilometers per second. Fritz Zwicky discovered it in 1941. Guyans called it one of the most complicated structures awaiting its explanation on the basis of stellar dynamics. He was right. The Cartwheel used to be a normal spiral like the Milky Way. Then a smaller intruder galaxy, probably one of 2 companions visible to the right in images, careened straight through its core. Not a glancing blow, dead center, like dropping a rock in a pond. The collision sent a gravitational shock wave expanding outward at 322,000 kilometers per hour. That's 200,000 miles per hour. The expanding ring sweeps up gas and dust, compressing it, igniting massive star formation. The wave leaves behind a firestorm. Hubble resolves bright blue knots, gigantic newborn star clusters, and immense loops blown into space by supernovae exploding like a string of firecrackers. The ring structure is double, bright inner ring, colorful outer ring expanding from the collision center. Both rings expand outward like pond ripples. The outer ring measures 150,000 light-years across. The entire Milky Way fits inside. The ring contains at least several billion new stars that wouldn't have formed in such a short span without the collision. Collision age estimates vary. Higdon, in 1996, analyzed HI velocity fields, inferred 300 million years since impact. AMRAM in 1998 used H-alpha kinematics with expansion velocity, 13 to 30 kilometers per second. Suggested over 200 million years. Renaud simulations in 2018 give shorter timescales, under 100 million years for ring persistence. James Webb observations from August 2022 show the ring has been expanding for about 440 million years. Recent stellar population analysis published in Astronomy and Astrophysics August 2024 reveals the outer ring is completely dominated by stars formed not earlier than 400 million years ago. The collision shockwave drags already formed stars outward while sweeping inner areas. The blue galaxy among the companions shows disruption and new star formation, strong evidence it's the interloper. The smoother companion has no gas, consistent with gas being stripped during passage through the cartwheel. The paradigm case for ring galaxies. Collisional ring galaxies form when a compact galaxy plunges almost perpendicular into a large gas-rich disk galaxy, impact point near center. The density wave moves outward radially, compresses gas, triggers star formation along a circular ring, leaves aging stellar population in its wake. Milky Way and Andromeda. The collision everyone talks about, everyone gets the timing wrong. Andromeda is 2.5 million light years away, approaching at 110 kilometers per second as indicated by blue shift. Until 2012, nobody knew if collision was definite. Researchers used Hubble to measure star positions in Andromeda in 2002 and 2010 relative to hundreds of distant background galaxies. Averaged over thousands of stars, they obtained average proper motion with sub-pixel accuracy. Conclusion: Andromeda moves southeast in the sky at less than 0.1 milliarc seconds per year, corresponding to a speed relative to the Sun of less than 200 kilometers per second, towards south and east. Taking Sun's motion into account, Andromeda's tangential velocity relative to Milky Way is much smaller than approach speed, consistent with zero given uncertainty. They'll merge in around 4 to 5 billion years, not 3.9 billion like old estimates said. European Space Agency's Gaia spacecraft data from February 2019 pushed the timeline back 600 million years. Roland van der Marel at Space Telescope Science Institute led the study. Published in Astrophysical Journal, February 7, 2019, Gaia does astrometry, scanning the sky repeatedly, observing each of its billion-plus targeted stars, an average of 70 times over 5 years. That gives actual data on star motions through space. The collision will likely be a glancing blow, not the head-on crash previously predicted. But wait, new research from 2025 by Tilsawala and colleagues complicates everything. When gravitational pulls from both Large Magellanic Cloud and Triangulum Galaxy are taken into account, something only possible with Gaia and Hubble data unavailable in 2012, the chance for collision is much lower. 50% probability of no collision during the next 10 billion years. Published June 2025 in National Geographic coverage. The merger might not happen at all. If it does happen, here's what we know. Andromeda contains about 1 trillion stars. Milky Way about 300 billion. Chance of even 2 stars colliding is negligible. Nearest star after the Sun is Proxima Centauri, 4.2 light years away, about 30 million solar diameters. To visualize, if the Sun were a ping-pong ball, Proxima Centauri would be a P about 1,100 kilometers away, and the Milky Way would be about 30 million kilometers wide. Stars near galactic centers are more common, but average distance between stars is still 160 billion kilometers. That's analogous to 1 ping-pong ball every 3.2 kilometers. Earth won't survive to see it anyway. The surface will become far too hot for liquid water in about 0.5 to 1.5 billion years due to gradually increasing solar luminosity. By collision time, the Sun's luminosity will have risen 35 to 40%, likely initiating a runaway greenhouse effect. When the collision happens, if it happens, there will be little gas remaining in both galaxy disks, so the starburst will be relatively weak compared to gas-rich collisions, though possibly enough to form a quasar. Simulation timeline from NASA published in 2012, at 3.75 billion years, Andromeda and Milky Way prepare for initial collision. At 3.85 billion years, the sky brightens from emergence of newly formed stars. At 3.9 billion years, clouds of ionized gas fill the sky. At 4 billion years, Milky Way appears warped, Andromeda stretched following first encounter. At 5.1 billion years, the cores appear as a pair of bright lobes. At 7 billion years, they combine into a huge elliptical galaxy. Some call it Milkomeda. 50% chance the solar system gets swept out 3 times farther from galactic core than current position. 12% chance of complete ejection from the newly formed galaxy. The Sun is currently in the Orion spur branch. If flung farther out, we'd land at the fingertips of the spiral arm. If we survive, which we won't, minor mergers follow different rules. Galaxy cannibalism. The Milky Way is eating smaller galaxies right now. Canis Major dwarf galaxy, possibly the Magellanic Clouds. The Virgo stellar stream is thought to be remains of a dwarf galaxy, mostly merged already. When a large galaxy strips material from, or completely swallows a smaller one, the larger stays largely intact. The smaller gets torn apart, becomes part of the larger galaxy's mass. Studies using Gaia data from June 2024 reveal the Milky Way's last major merger, the Virgo radial merger, happened much more recently than previously thought. Not 8 to 11 billion years ago, within the last few billion years. The old theory said the Gaia Sausage Enceladus merger happened when the Milky Way was in infancy, infusing stars on orbits bringing them close to galactic center. Gaia Data Release 3 from 2022 suggests these oddly orbiting stars were deposited by a different, more recent merger event. Thomas Donlan at University of Hertfordshire said, "This result, that a large portion of the Milky Way only joined us within the last few billion years, is a big change from what astronomers thought up until now. The Virgo radial merger likely brought a family of other small dwarf galaxies and star clusters, all devoured by the Milky Way around the same time. Up to 50% of mass in galaxies today comes from previous galaxies cannibalized. Christopher Consolis at University of Manchester confirms it. The Milky Way shows evidence of assembly via multiple galactic smash-ups. Sagittarius dwarf elliptical galaxy is diving into the Milky Way right now. Streams of gravitationally attracted hydrogen arcing from dwarf galaxies to the Milky Way prove ongoing cannibalism. Ultra-compact dwarfs represent late-stage victims. Researchers using Gemini North Telescope near Mauna Kea in Hawaii spotted galactic cannibalism near the Virgo cluster. In November 2023, a large grouping of thousands of galaxies relatively nearby to Earth, 106 galaxies, exhibited far-reaching envelopes of stars, suggesting outer layers being ripped apart by nearby large galaxies. Tight groupings of stars in their centers reveal gravitational grip strong enough to survive the merger. After outer stars and gas are pried out, the tiny galaxies become late-stage, ultra-compact dwarfs. Eric Peng at National Optical Infrared Astronomy Research Laboratory said, "It's exciting that we can finally see this transformation in action. It tells us that many of these UCDs are visible fossil remnants of ancient dwarf galaxies and galaxy clusters. Starburst galaxies represent collision's most violent creative phase. When galaxies collide, if either contains interstellar matter, the collision compresses gas and triggers increased star formation rate by as much as a factor of 100. Astronomers call this a starburst. The galaxies where it occurs are starburst galaxies. Star formation rate during a starburst can reach hundreds of solar masses worth of new stars per year. Typical Milky Way makes about 2 to 3 new stars per year. Starburst galaxies make 300. M82 is a starburst galaxy, passed close to spiral galaxy M81. Rapid star formation and supernova explosions from massive stars in M82 ejected a huge plume of material from galactic center. The antennae are both undergoing starbursts. In some interacting galaxies, star formation is so intense all available gas exhausts in only a few million years. The burst is temporary. While it's going on, the galaxy becomes much brighter, much easier to detect at large distances. Infrared astronomical satellite, IRAS, launched in 1983, revolutionized starburst detection. Most action is obscured behind thick dust clouds, difficult to penetrate at visual wavelengths. IRAS provided accurate measures of energy generated within these objects, showed merging galaxies are among most intrinsically luminous objects in the universe. IRAS detected colliding galaxies solely on infrared emission over vast distances, gave first accurate census of galaxy mergers over cosmic time. Some collisions were so far their light was emitted when universe was 1/5 current age. In some merging galaxies, more than 90% of total power output occurs at far infrared wavelengths, their true natures completely hidden from optical telescopes. IRAS discovered luminous infrared galaxies, LIRGs, ultraluminous infrared galaxies, ULIRGs, have luminosities greater than 10 to the 11th solar luminosities. Physical mechanism behind starbursts during typical collision between two field spiral galaxies. HI clouds from both undergo collisions at relative velocity around 300 kilometers per second. Giant molecular clouds with smaller volume filling factor E don't collide. But the HI cloud collisions create dense, shocked layers that gravitationally destabilize the GMCs, triggering massive star formation burst in initially barely stable GMCs. Resulting typical infrared luminosity from young massive stars from a pair of colliding galaxies estimated at 2 × 10 to the 11th solar luminosities. That agrees with observed values. Published in Astrophysical Journal in 1992, Cloud-cloud collisions trigger star formation in the form of massive clusters due to enhanced external pressure. The process creates massive stars. Although difficult to track individual gas structures in simulations, presence of thin, dense tidal tails and bridges connecting density peaks confirms ubiquity of cloud-cloud collisions. A significant fraction of star formation activity in overlap regions linked to cloud-cloud or cloud reservoir collisions. In galaxy nuclei, gas gets fueled toward the center by negative gravitational torques, mainly from one galaxy acting on the other. Clumpy nature of fueled material makes nuclear accretion comparable to series of cloud-cloud collisions. Star formation enhancement from mergers is less than factor of 2, according to careful statistical analysis published in Astrobytes in 2019 using convolutional neural networks trained on SDSS, on KEDS, and Candle's survey data. Despite rapid increase in star formation, magnitude of burst is not great enough for merging systems to become differentiated from non-merging population based solely on star formation rate. Starburst episodes are short-lived relative to timescale required to complete merger. Merger sequence is much longer than individual episode of starbursting, so starburst episode usually missed by observations. However, extreme starbursts are commonly merging systems. Illustrious TNG simulations examined galaxy interactions across redshift ranges 0 to 15. Patton in 2020 explored link between increased star formation and nearby companion galaxies. In TNG 100-1 simulation, average specific star formation rate boosted by factor of 2.0 plus or minus 0.1 at separations smaller than 16 kiloparsecs. In TNG 300-1 simulation, consistent enhancement in mean specific star formation rate across redshift range 0 to 1. When galaxies have nearby star-forming companions, they exhibit significantly higher specific star formation rates by factor of 2.9 plus or minus 0.06 compared to isolated counterparts. These enhancements evident out to large separations. Bottrell in 2024 presented large public dataset of over 750,000 synthetic galaxy images from TNG 50 and TNG 100 simulations. Investigated how different merger types, major R, minor R, mini, relate to galaxy asymmetry and star formation activity. Found mini mergers, despite small mass ratios, are primary drivers of enhanced asymmetry and elevated star formation rates. Published September 20 to 24 in ArXiv preprint. Peak of star formation rate is observed at higher redshift than previously examined studies covered. Impact of galaxy collisions changed in early universe. Study published September 11/20/25. ARP 107 shows another collision type located 465 million light-years away in Leo Minor constellation. Interaction between elliptical galaxy and spiral galaxy. James Webb Space Telescope observed it. September 20 to 24. NIRCam highlights stars within both galaxies, reveals connection between them, transparent white bridge of stars and gas pulled from both during passage. MIRI data in orange-red shows star-forming regions and dust composed of soot-like organic molecules, polycyclic aromatic hydrocarbons. MIRI provides snapshot of bright nucleus of large spiral, home to supermassive black hole. Spiral classified as Seyfert galaxy, one of two largest groups of active galaxies, along with quasars. Seyfert galaxies aren't as luminous and distant as quasars, making them more convenient for studying similar phenomena in lower energy light. The collision occurred hundreds of millions of years ago. Smaller elliptical galaxy likely had off-center collision instead of direct hit, so Spiral got away with only spiral arms being disturbed. Although there was star formation before, collisions compress gas, improving conditions for more stars to form. On the other hand, collisions also disperse a lot of gas, potentially depriving new stars of material they need. Webb captured these galaxies in process of merging, which will take hundreds of millions of years. As two galaxies rebuild after chaos, ARP 107 may lose its appearance, but will turn into something just as interesting. Previously observed by Spitzer Space Telescope in 2005, but Webb displays much higher resolution. Galaxy harassment occurs in rich galaxy clusters like Virgo and Coma, where galaxies move at high relative speeds, suffering frequent encounters with other cluster systems due to high galactic density. According to computer simulations, interactions convert affected galaxy disks into disturbed barred spiral galaxies, produce starbursts, followed by, if more encounters occur, loss of angular momentum and heating of gas. Result is conversion of late-type low-luminosity spiral galaxies into dwarf spheroidals and dwarf ellipticals. String of pearls formation in tidal tails, Hubble Space Telescope in March 2025, traced 12 interacting galaxies with long, tadpole-like tidal tails of gas, dust, and plethora of stars. Hubble's sensitivity to ultraviolet light uncovered 425 clusters of newborn stars along these tails, looking like strings of holiday lights. Each cluster contains as many as 1 million blue newborn stars. When galaxies interact, gravitational tidal forces pull out long streamers of gas and dust. Antennae in mice galaxies are popular examples with long, narrow, finger-like projections. A team of astronomers used a combination of new observations and archival data to get ages and masses of tidal tail star clusters. Black hole mergers accompany galaxy mergers. When galaxies collide, supermassive black holes at their centers eventually merge. NGC 6240 shows 2 bright X-ray sources near center, likely locations of 2 supermassive black holes inhabiting cores of 2 galaxies pre-merger, participating in death spiral where 2 black holes themselves will merge to become one, published by Chandra X-ray Observatory. Very large elliptical galaxies probably form by cannibalizing a variety of smaller galaxies in their clusters. Monster galaxies frequently possess more than one nucleus, probably acquired unusually high luminosities by swallowing nearby galaxies. Multiple nuclei are remnants of victims. Shell structures around galaxies indicate recent merger. VCC 848, a blue compact dwarf galaxy in outskirts of Virgo cluster, 65 million light-years away, shows complex set of 3 extended shell-like structures of stars around bright stellar main body. Shells previously only detected in larger galaxies. Their signature of recent minor or major galaxy merger, formed as merger, sends ripples through galaxy and disrupts structure. Detection of shells in such small galaxy provides evidence of recent merger of 2 dwarfs. Hongxin Zhang at University of Science and Technology of China led study published in 2020 using MegaCam instrument on Canada-France-Hawaii telescope in Hawaii. 2 dwarfs that collided were likely similar in mass to within factor of few. Merger triggered burst of star formation over past billion years that was 7 to 10 times higher than normal. Enhancement peaked near center a few hundred million years ago, since declined. First direct observation of merging star clusters in nuclear region of dwarf galaxies published in Nature April 9, 2025, led by Melina Poulin from University of Oulu, Finland. While studying observations of nearly 80 dwarf galaxies from Hubble Space Telescope, researchers noticed handful with unusual-looking nuclear star cluster. Some showed couple star clusters close together, others had feature similar to faint stream of light attached to nuclear star cluster. Analysis showed they have similar properties to globular clusters already detected in dwarf galaxies. Observations witnessed growth of nuclear star cluster by dramatic cannibalization of globular clusters at cores of galaxies. Ultra-high resolution complementary simulations, led by Rory Smith at Universidad Técnica Federico Santa Maria in Santiago, confirmed light streams created by 2 star clusters with significant mass differences merged. Larger the mass ratio, longer the stream. Process lasts less than 100 million years. Features visible for even less time. That's why catching them is rare. One final data point that reframes the whole picture. Recent Hubble measurement of Gaia sausage and Celadus merger remnants, published June 2024, showed something unexpected. The merger that astronomers thought happened 8 to 11 billion years ago, when Milky Way was young and violent, actually happened within last few billion years. We get wrinklier as we age. The opposite is true for Milky Way. It's a cosmic Benjamin Button, getting less wrinkly over time. Large portion of Milky Way only joined us within last few billion years. That changes models of how Milky Way grows. Many popular models would expect recent head-on collision with dwarf galaxy of this mass to be very rare, but it happened. Recently, the universe is not stable. Galaxies are not fixed. They crash at millions of kilometers per hour. They rip each other apart. They ignite cosmic firestorms. They merge into new forms. The Milky Way has done it before. It's doing it now with dwarf galaxies orbiting our halo in 4 to 5 billion years. Maybe it'll do it again with Andromeda, or maybe they'll miss. 50-50 chance. Either way, the collision has already started. The halos are touching. The gravitational dance began. We're just waiting for the impact. Every collision type explained. Head-on bullseye strikes creating expanding rings. Glancing blows, tearing tidal tails, hundreds of thousands of light-years long. Minor mergers where small galaxies get shredded and consumed. Major mergers where comparable spirals smash together and ignite starbursts, creating hundreds of solar masses worth of stars per year. Dry mergers in dense clusters where gas-poor galaxies merge without fireworks. Off-center collisions, disturbing spiral arms but leaving cores intact. Penetrating encounters where one galaxy punches through another's disk. Satellite galaxies diving into primary galaxies, triggering small bursts of star formation. Multiple collisions in groups creating complex debris fields. Ring galaxies with double expanding halos. Starburst galaxies burning through their gas in mere millions of years. Shell structures rippling outward from merger sites. Tidal bridges connecting colliding pairs. String of pearls, star clusters, forming in stretched tidal tails. Supermassive black holes spiraling toward merger. Ultra-compact dwarfs, the fossil remnants of ancient cannibalism. The data is there, the observations are documented, the physics is brutal and beautiful. Stephan's quintet observed November the 2024 by Weave spectrograph. Antennae age-dated by Hubble showing 10% cluster survival rate. Mice simulations by Barnes and Hibbard pinpointing 160 million years post-encounter. Cartwheel ring expansion, tracked by James Webb showing 440 million year evolution. Milky Way Andromeda collision timeline revised by Gaia spacecraft February 2019. Virgo radial merger detected in Gaia data release 3/2022. String of pearls clusters counted by Hubble March 2025. 425 newborn star clusters. VCC 848 shell structures imaged 2020. Dwarf galaxy star cluster mergers captured by Hubble April 2025. Every measurement documented, every source cited. The collisions continue. Right now, NGC 7318b is tearing through Stephan's quintet at 3.2 million kilometers per hour, leaving a glowing trail of ionized gas. The antennae are forming superstar clusters by the hundreds. The mice are pulling 300,000 light-year tidal tails across the cosmos. The Cartwheel's outer ring is expanding at 322,000 kilometers per hour. The Milky Way is consuming the Sagittarius dwarf. Andromeda is racing toward us at 110 kilometers per second. The halos already touch. This is galaxy evolution. Not gradual, not gentle, violent, fast on cosmic scales, inevitable. The universe expands, but gravity still binds neighbors close enough to collide. Collisions were more common when universe was smaller, galaxies closer together. They're rarer now. Still happening. 5% of nearby galaxies currently involved in interactions. That's published data, 1 in 20. Look at enough galaxies, you'll find the wrecks. And here's what they never tell you about the numbers. Density of air at sea level on Earth is about 100 million billion times greater than average density of gas in interstellar space. When astronomers say galaxies collide, the stars don't touch. 300 billion stars passing through 300 billion more. Almost none collide. The distances are too vast. If the sun were a ping pong ball, nearest star is a peak of 1,100 kilometers away. But the gas collides, the dust collides, the magnetic fields tangle. Shock waves propagate, molecular clouds compress, stars ignite, supernovae explode, more shock waves, chain reaction. That's the violence. The final piece, ARPA 220, ultraluminous infrared galaxy, well-studied UL-IRG, X-ray observations, penetrate dust, suggest many starburst galaxies are double-core systems. That supports hypothesis, UL-IRG is powered by star formation triggered by major mergers, more than 90% of power output in far infrared wavelengths. True nature, hidden from optical view. IRAS found thousands of these. They were common billions of years ago when galaxies were closer, collisions more frequent, less common now, but still there. Submillimeter galaxies at high redshift or over 2 are UL-IRGs, or hyperluminous infrared galaxies with luminosities greater than 10 to the 12th solar luminosities. The universe was more violent then. Galaxy evolution is a collision history. Elliptical galaxies, the smooth, old red systems with no spiral structure, are merger products. Simulations confirm it. Observations support it. When two gas-rich spirals merge, they burn through their gas in a starburst, form elliptical. Slow collisions and mergers can transform 2 or more spirals into a single elliptical galaxy. The very large ellipticals probably form by cannibalizing variety of smaller galaxies. Many large peculiar galaxies owe chaotic shapes to past interactions. The Milky Way itself is merger product. Up to 50% of stellar mass from previous cannibalized galaxies. Toomre sequence demonstrates collision stages. Aller-Toomre and Jury-Toomre, American astronomer and mathematician and astrophysicist brothers, used antennae ARP 295 in Aquarius, Whirlpool Galaxy Messier 51, and NGC 5195 in Canes Venatici, and mice galaxies in Coma Berenices to create models in 1970s. First simulations of galaxy mergers. The sequence shows how morphologies evolve through collision phases. Initial approach, first passage creating tidal tails, separation phase, return passage, final merger, Takes hundreds of millions to billions of years depending on initial conditions. Velocities, angles, mass ratios, collision geometry matters. Head-on collisions create ring galaxies like cartwheel. Glancing blows create tidal tails like antennae in mice. Off-center hits disturb spiral arms, but preserve cores like ARP 107. Penetrating encounters create shock fronts like Stephan's quintet. Minor mergers strip smaller galaxy-leaving tidal streams. Major mergers between comparable galaxies trigger intense starbursts and eventual elliptical formation. Each geometry produces different morphology. Different star formation rate, different outcome. Mass ratio determines violence. Major merger defined as two galaxies of similar size. Typically, mass ratio better than 1 to 4. These are most disruptive, most likely to trigger starbursts, most likely to form ellipticals. Minor mergers have one galaxy significantly larger. Larger one often eats smaller with little effect on larger galaxies' structure. Galactic cannibalism. Mini mergers have even smaller mass ratios, but illustrious TNG simulations show their primary drivers of enhanced asymmetry and elevated star formation rates, despite small size. Gas content determines brightness. Gas-rich collisions trigger starbursts. Gas-poor dry mergers in dense clusters merge without fireworks. Milky Way Andromeda collision will likely be relatively weak starburst because both will have little gas remaining by collision time. That's 4 to 5 billion years from now. Both galaxies have been forming stars for 13 billion years by then. Most gas consumed, still enough for possible quasar formation from merged supermassive black holes. Timing is everything. Starburst episodes last tens of millions of years. Merger process lasts hundreds of millions to billions of years. That's why most merger observations miss starburst phase. Starburst is brief relative to merger timescale. But when you catch it, M82, antennae, ARP 220, it's spectacular. Hundreds of solar masses per year. 300 times Milky Way rate. Burn through all available gas in few million years. Then it's over. Galaxy is gas poor, red, quiet, old elliptical, one more measurement, Virgo cluster galaxy harassment, high-speed encounters in dense clusters, galaxies moving at high relative speeds, frequent encounters due to high galactic density. Simulations show interactions convert late-type spirals into dwarf spheroidals and dwarf ellipticals. Published results confirmed by observations. 106 galaxies in Virgo cluster exhibit far-reaching stellar envelopes from ongoing stripping. Transformation in action. This is the complete picture. Every spectacular type of galaxy collision. Head-on rings, glancing tail pullers, minor cannibalism, major starbursts, dry mergers, off-center disturbances, penetrating shocks, satellite dives, multiple collision debris, shell structure remnants, tidal bridges, pearl string clusters, black hole spirals, ultra-compact dwarf fossils, galaxy harassment, each type documented, each mechanism understood, each observation dated and sourced. The universe keeps colliding. Galaxies keep merging. The Milky Way keeps eating smaller neighbors. Andromeda keeps approaching at 110 kilometers per second. Maybe they'll collide. Maybe they'll miss. Either way, the physics doesn't care about maybe. It cares about mass, velocity, angle, gas content, distance. Feed those into equations, watch the simulation, see what happens. Hundreds of simulations run, thousands of observations made. The data points to one thing. Collision is fundamental to galaxy evolution. Always has been. Always will be. Until the universe expands enough that galaxies are too far apart to interact. But we're not there yet. Not for billions of years. Right now, they're still close enough, still colliding, still merging, still creating, still destroying. NGC 7318b at 3.2 million kilometers per hour. That's the speed of galaxy collision. That's the speed of cosmic evolution. That's the speed we need to understand if we want to know how the universe works. Final data point. From James Webb Observation of Cartwheel Galaxy, published August 2022. Webb's infrared instruments unveil details obscured in previous observations. The galaxy is in very transitory stage. It was presumably normal spiral before collision. Will continue to transform. While Webb gives a snapshot of current state, it provides insight into what happened in past and how it will evolve in future. Transitory. Everything is transitory. Even galaxies, especially galaxies. They crash, they merge, they transform. The cartwheel will not stay a ring forever. The spokes are already reforming between outer ring and nucleus, faint spiral arms emerging. The galaxy is trying to rebuild, trying to become spiral again. It might succeed, or another collision might interrupt. The universe doesn't offer guarantees. That's galaxy collision. Every spectacular type explained, every mechanism documented, Every measurement cited, from 3.2 million kilometers per hour shock fronts to 100 million year tidal tail formation. From 10% superstar cluster survival rates to 7 to 10 times enhanced star formation and dwarf mergers. From 425 pearl string clusters and tidal tails to 50% chance of no Milky Way. Andromeda collision in next 10 billion years. The numbers are there. The physics is there. The observations are there. This is what happens when 300 billion stars meet 300 billion more. This is collision. This is evolution. This is the universe.